until fairly oops, okay. I got a little interruption here. So, okay. Until recently, I would always thought of data reliability in terms of the great Wikipedia scientific reference source, in terms of things like the consistency of the data and what kind of techniques and procedures were used to collect data. But then I became aware that there's actually a fairly, well, in my kind of perspective, a fairly large amount of data out there which have integrity problems in terms of they may be falsified, they may be fabricated. And so I think that data integrity problems are something that are vastly underappreciated in the chemistry community, gets a fair amount of attention in the biologic community, biomed community, but I think it's mostly neglected, and people should pay more attention to the possibility of the data that they're reviewing as being not real, not authentic. Okay, so in the US, not the US, in the world in 2020, there were roughly 3 million scientific and engineering papers published. And of those, about 6%, or nearly 180,000, were in chemistry. So of those, roughly 0.04% were retracted due to scientific misconduct. So that's a floor on the number of falsified chemistry papers that were published in 1 year. On the upper end of the range, the number is probably closer to 4%. And that number is based on the work of Dr. Elizabeth Bick, and I've put the URL to her blog down at the bottom. She's a biologist, and she has fantastic pattern recognition skills, let's say. And so she's gone through many thousands of mostly biology papers, biomed papers, and found evidence of things like image duplication, because the biology fields apparently involve a lot of image analysis. And so a lot of those papers have things like Western blots, and people look at the sizes and shapes of these things and they get some sort of biologic information out of them. And there's other things, some of them which are more similar to analyses done in chemistry, but the figures and papers frequently have obviously been photoshopped. And so she picks these things up both within papers and between papers. And after all the thousands of papers she's looked at, she's arrived at this number of roughly 4%. And I don't think biologists are any more dishonest or honest relative to the chemistry community. So I've taken that 4% and shifted it back over to chemistry. And if you do that, somewhere in the neighborhood of 7,000 papers a year in chemistry are basically fraudulent. It's a lot of papers. So recently, there's been a lot of attention given to scientific misconduct, science misinformation, largely related to COVID, because anytime you throw huge amounts of money at something, you're going to get some number of crooks that follow the money. And so most of the popular mainstream media kind of attention given to scientific misconduct has focused on biology, but I reference a recent paper that specifically addresses misconduct in chemistry papers over the past 20 years down here. So I suggest people might want to look at that sort of thing. And they found that over the past 20 years, 60% of the retractions have been due to misconduct. And that involves things like just flat out fraud, things like fabrication, self-plagiarism, plagiarism of other people's works. So that's I just suggest that people pay attention to that sort of thing. Now, what's the impact? Well, there's a huge amount of money spent on US. And so these are just US numbers. And the EU is roughly the same order of magnitude, maybe a tad larger. But in the US in 2019, roughly $600 billion spent on R&D work. And of that, I don't want anyone to think that because most of that money is coming out of industry, that it's not real, honest to God, fundamental science kind of work, because roughly 25% of the money in basic research came out of industry. So it's a large amount of money from both federal government and industry that are spent on real, honest to God science as well as more applied science. So if you take that 0.4 or the 0.04% number and multiply it by that total, the floor on wasted expenditures on R&D spending is $55 million a year. That's the baseline, and that's a large amount of money in itself. If you apply the 4%, you're up closer to $5 billion. That's a lot of money. So, you'd think that the government as well as industry would be paying attention to the amount of work that they're paying for in R&D spending that is wasted due to fraud. So what's the impact? Well, one is that it's taken money away from ethical scientists that want to do actual science with their money. Scientists are always griping about the lack of funding. And before we even started this, we got a little bit of that. So the money that's wasted is not money that's going to science. And fraud in science is just like fraud in the banking industry or investment community. When it's found out, people start putting a lot of other funding towards oversight to make sure it doesn't happen again. Well, that's an additional cost that, again, is taking money away from science and scientists. Another thing is engineering failures. Most scientists, when they write a grant proposal or write a paper, they put in some statements about some practical application of their work. Well, if that science is adopted in application and it's fraudulent, it can contribute to engineering failures. And one of the cases that I took out of this presentation was one where the chief metallurgist at a company that made steel, specialized steel for US nuclear submarines, fabricated her testing data for 32 years. And that's another thing that happens. These things can go on for a long time, and they can affect broad swaths of things that affect society. And so, in a submarine, if you happen to be a sailor and you're down at 800 feet deep in the ocean and the hull gives way because somebody fabricated the metallurgical data, that built your submarine, you're going to be mighty unhappy. And if you lose some nuclear missiles at the bottom of the ocean, that makes governments unhappy. So, these are real actual consequences to people and things and the environment. So it's another thing. So then you get loss of industrial competitiveness. If you're a company and you've got somebody making up fraudulent data that you're using to help make your company more competitive and it turns out to be fraud, well, all you've accomplished is making your competitor. You've given an advantage to them. And the same thing applies to countries. If you're a country and you've got a bunch of fraudsters operating in your research community, your country is wasting money and losing competitiveness to other countries that might not be as friendly to you. And finally, there's the loss of confidence in the lay public on science. And again, that is particularly evident during COVID, where you had a lot of fraudster scientists running around claiming cures and treatments for COVID. A lot of money was spent on that. won't get into any political comments, but it's very divisive. Um, Lots of people, they go with who they believe is telling the truth with regard to science, and some of those people aren't real honest to God legitimate scientists. And eventually, when that all comes out, creates loss of confidence problems. So what can be done about it? Well, in the US, there are laws about scientific misconduct, but be civil um, uh, complaints. So people are pursued criminally as well. And I've got a long list of examples here. These are just federal scientific misconduct cases. And the top one is Lawrence Livermore National Lab scientist who falsified his measurements for a while. And the federal government went after him, prosecuted him, put him in jail for 18 months, and forced him to pay back $3.3 million. And for most scientists, having to cough up $3.3 million would be a pretty big ding in the pocketbook. Not to mention the inconvenience of spending a year and a half in jail. Now, as I said a minute ago, scientific misconduct is not a crime, it's a civil offense, but this guy went to jail. And so when he went to jail for was doing things like lying to federal officials and falsifying his data and putting it in the mail to those federal officials, because those things are crimes. And so judges, juries, lawyers, they don't like to deal with science. Most of them don't know the first thing about science, so they don't pursue scientific misconduct itself. They go after related things that sometimes are crimes, but they are easier to pursue. So lying to federal officials is a crime. You can go to jail for it. Now, the second example here is Duke University, and they've had a couple of big scientific misconduct cases, and I've just listed the most expensive of them. And it costs the university $112.5 million. That's a lot of money. Well, it's a fraction of the total amount of grant funding that was affected by the frauds that were related to this. Now, the total amount of money related to the fraudulent research was $600 million. They settled for roughly 20% of that. And by settling, they get to continue to evicted. There was a chance that they would have been barred from receiving any future grant money. So this is a little thing that companies and universities, various research institutes do in the US when they're caught doing scientific misconduct. They usually end up settling for a fraction of the real cost of the infractions. Now, another little thing associated with this that shows how small investigations can morph into big investigations. That Duke case started out as an embezzlement investigation where a lab technician was thought to have stolen a few $1,000s. Well, that few $1,000s of embezzled money turned into $112 million ding to the university. So what is falsification? So this is the federal law, US federal law, that defines what falsification is. Now, there are different types of scientific misconduct. One is fabrication, where you're just making the data up out of thin air. One is plagiarism, which also is fairly self-explanatory. And then there's falsification, which is a little broader and a little fuzzier. And it applies to lots of different things you can do to change your data. But the bottom line is that you're changing methods or data or procedures so that they don't actually represent the truth. Now, what is the significance? What can, I give an example here of brucite measurements. So if you do some brucite magnesium hydroxide solubility experiments, you publish the work, and nowhere in the paper do you disclose that you did the experiment on a benchtop and the experiment was exposed to CO2. And so what you're measuring is a different chemical system than what you've disclosed. Is that falsification? And so I would say, well, by strict construction of the definition, it would be yes. But by historical standards, I'd say no, because dozens of people have measured brucite solubility on benchtops and not bothered to mention that it was exposed to CO2. And you can back calculate the effect of the CO2. So the federal government isn't going to pursue that particular case. What is falsification is if you do an experiment on some borate mineral solubility and you've got 6 samples in your study and you leave out 4 of them because the results of those 4 studies happen to show something quite different from your preconceived hypothesis and conclusion. Another example is if you measure borax solubility and you don't mention the fact that you have solid neodymium hydroxide in your experiment, and you present that work in a published paper as borax solubility, but the real study was initially designed to be a neodymium hydroxide solubility study, and you've basically repurposed your results and the study. These are real examples that I'll get to. So this is the first case. This is the borax solubility or purported borax solubility study. Nowhere in the paper does it mention neodymium. Yet if you look at the data table, and this is what got my attention, I've done some work on borate thermodynamics. And so I looked at this paper and I looked at the table of data. And the first thing I saw was this red box down here. The red box is mine. But the sample IDs all begin with NDOH3 with the 3 subscripted. And to most of us, that would look suspiciously like neodymium hydroxide. And I thought, why is a guy that's publishing a paper on borax solubility got sample IDs that begin with a prefix of neodymium hydroxide? Looked very odd to me. So I went back and I know this guy's work, and I know he's done some work on neodymium hydroxide, and I know that that work is also in the government report literature. So I searched for those sample IDs, and I found this. And at the bottom down here is a table. It's excerpted from government report that I found, and it has these sample IDs down here. And this is another excerpt on the top from the published paper, and you can see that the sample IDs are the same. So this is just part of the data tables from both reports. Top one's published, the bottom one's in a government report, which strictly speaking is also published. And it's got the same sample IDs. If you look at the sampling time's the same. And the government regulations in this case disallow a contractor from reusing sample IDs. So if you reported these sample IDs to the US government, then you can't reuse those sample IDs for a different experiment. They have to be the same. So they reported 2 different things. Well, they reported the same thing as being 2 different things. So that's, to be kind, misleading. This is my first example. Oh yeah, and the government report, they make it quite clear, and you can look at the table heading here. It's quite clear that the experiment contains neodymium hydroxide, And the purpose of the study in the government report is to evaluate the effect of borate on neodymium hydroxide. So again, this guy repurposed his study, published it as something different than its original intent, and didn't bother to mention that he had other stuff in his samples. That's falsification. So here's another case that I discovered along the way where you have overly similar data. And on the left, I've got two data sets, one from 1955 and a more recent one, so roughly 60 years later. These are isopiastic data for an organic acid. So I've plotted them as osmotic coefficients versus, I'm not going to get into the details of which organic acid. But the more recent study, which is these red circles, strangely overlap almost identically with the older study. So the newer study has about 20 results. The older one has about 26. The newer one overlies nearly identically with 20 of the 26 original data measurements. Now on the right, I've added a couple of other studies, same system, same chemical system over the same range, X and Y axes, and they show what you would expect from isopiastic measurements in this system. Particularly below 1 molal, you see greater spread in the data. You see points that lie between the other points. This is the sort of thing you would expect from isopiastic measurements, because in an isopiastic measurement, you're basically adjusting both variables, both the dependent and independent variable are shifting. And so getting both of those variables to lie on top of each other, go out and buy yourself a lottery ticket, because if you can do that, you are one really extraordinary human being. So, I can't say that this newer guy actually falsified or plagiarized his data, but they are highly suspicious. And just as a final note, a lot of times fraudsters don't seem to cite original works. And that's the case in this case, where this guy with the newer study, he didn't bother to cite this older study. It's just a miracle that he happened to come up with the same numbers. I'm sure it's all above board. Okay, here's another case where we have some very similar data. On the left, this time I've plotted a whole bunch of different data sets for apparent molar volume versus calcium chloride molality. And you can see there's a fairly high degree of scatter, particularly down here. If you want to check out data sets just because they disagree, I'd check out this blue solid points down here and call the rest of these points measurement error. And it's larger than I would expect for some systems, but for this particular chemical system, it is what it is. Now over here on the right, we have the same scaling. So these two sets, two graphs are directly comparable. And the measurement conditions are a little bit higher temperature, which one might think to be a little bit more challenging. And because the measurement conditions are a little bit more challenging, you would expect a higher degree of error involved in the measurement. But lo and behold, where these two different studies overlap, the data points overlap almost identically again. And one might think, well, that's just two measurement conditions and it's just two pairs of measurements. It's possible. The problem is that there are 7 isotherms, because these both studies measured identical conditions over 7 temperatures, and they're all like that. They're all identical. So again, I can't go out and say, gee, the newer guy's a fraud, but I can say that is awfully suspicious. Um, going up to 200 degrees and 20 bars, I've done these measurements myself with the same chemical system. My own measurements don't have that kind of precision. So, just very odd. Now we get to another case. Now, in this case, this is one that where I look at it and I say, these data just don't make sense. Either the data are bad or there's something other than what they claim to be. So this is a purported case of lead oxalate solubility in sodium chloride solutions. And in this chemical system, there are activity coefficient models for sodium chloride. There are activity coefficient models for the oxalate systems. It may not be perfect, but they're good enough. There are equilibrium constants for solid lead oxalate and complexation constants for lead oxalate solute species. You should be able to reproduce these data from existing model parameters. But this black line here is that model. It uses a good oxalate activity coefficient model, a good sodium chloride activity coefficient model, and it uses good enough lead oxalate solubility constants and association constants. Yet the model clearly misses the data. The solubilities are low enough, a thousandth of a mole, so that the addition of additional activity coefficient model parameters is unwarranted. So that's not the problem. The problem is that either these data are really bad or they are something different than what they're claimed to be. Now you look down here and look at this chemical reaction and you think, well, gee, you could form this. Well, this is a known solid. It's not a mystery. People have known. We'll go to the next slide now. No, it's a couple slides down. People have known for 100 years that this solid exists. There's lots of X-ray diffraction data, not so much thermodynamic data, but this isn't a mystery thing. There's nothing new about it. And so we'll get to this now. So I suspect that that's what's going on, that it's not the data are bad. I think that the data are just lead oxalate chloride rather than lead oxalate, and that the guy that claimed they were lead oxalate basically lied. So I went mining through the government literature again, looking for that sample ID again, and lo and behold, same result. This XRD scan over here on the right is from a government report. And the green lines here are the 2 theta values corresponding to the reference standard for lead oxalate chloride. So every peak in this X-ray diffraction scan for the same sample ID. That over here, this is a table from the published paper. Over here is a sample ID from the government report. You look at the XRD scan in the government report, every single peak matches up with the standard for lead oxalate chloride. So you think, well, gee, your suspicion is right that the solid in that experiment, once you get past this point down here, all these other points look like lead oxalate chloride. And sure enough, I just published or just pasted one XRD scan here, but all of the other XRD scans are the same way. For those high sodium chloride molality, they all show up as lead oxalate chloride rather than lead oxalate. So if you throw in a solubility constant for lead oxalate chloride, this is what you get. So this isn't a final version of what I've done here. This is just basically a crude first stab model, so it's not very pretty. But I just threw in a solubility constant for lead oxalate chloride at no other changes to the model. Everything else is the same. All I did was add a solubility constant, and lo and behold, the data are reproducible by a different model than the published one. And what I've shown down here is that the existence of this solid has been known for nearly 100 years. Again, no freaking mystery. Now, some people might say, well, you x-rayed these things years after the paper was published. Maybe they formed after the samples were stored and archived. Well, one of the things that these nearly 100-year-old papers show is that the stuff forms in a matter of minutes. The published study lasted 3 years. And anybody that thinks that that solid formed at 3.5 years or 4 years or 5 years, just because it sat around for a few extra months, you're basically blinding yourself. So that's another case. So the short story on that one is the data look to be fine, but they're just misrepresented. So this gets into what I was just talking about with, the people that bend over backwards to make excuses for apparently falsified data. They say, well, maybe that oxalate chloride formed during storage. Well, that's the point. I say, well, it's been known for 100 years that the stuff forms within minutes. Why do you think it would form at 3.5 or 4 years versus 3 years? The storage conditions were the same as the experimental conditions. There was still liquid in the stored samples. Just losing water from evaporation or diffusion through the sample container or through CO2 contamination, those things can't explain the formation of that other solid. It's the only solid in the sample. So if you're going to argue it's from contamination, where's the stuff that it's supposed to be contaminated? And the most damning thing is that the paper claims to have done solid phase analysis, yet there's not a single piece of evidence is presented in the paper to substantiate that claim. There's no XRD scans published in the paper, nothing. And so if somebody wants to refute the claim that those samples are fraudulent, where are these contemporaneous analyses that were supposedly done and the claim published? You want to show otherwise, you want to substantiate your work, prove it. And this is a common problem with what I call fraudsters. You ask them to provide the evidence. And in this case, they are required by the government to preserve that evidence. Where is that evidence? And they do things like claiming, oh, the dog ate it. We've lost it. Well, retract the paper then. So there's nothing about this. And the simplest explanation, I just pointed out down here, Occam's razor, is the simplest explanation is that those data are something different than what the author claimed they are. So here's another example. And this is the same individual. And this is another common feature amongst fraudsters. They tend to be repeat offenders. So in this case, he supposedly measured the solubility of a sodium hexaborate in magnesium chloride solutions. And if any of you are familiar with evaporite deposits, you might think, well, why would you form a sodium hexaborate by putting borax in a magnesium chloride solution? Because magnesium borates tend to be less soluble than the sodium borates. So just a first intuitive thought would be the title itself does not make sense. And so that's what I thought. So get on to some other things. So once again, I went through the government literature looking for sample IDs. So on the left is a table from the published paper, and the sample IDs, the prefix here is the magnesium chloride molality. So he measured two samples, one at 0.01 molal magnesium chloride and one at 0.1 magnesium chloride. And he just repeated the same measurements over and over again as a function of time. So in this third column here is the sampling interval. And so in the published paper, he says his first sampling interval is 20 days, the next one 68 days, 210 days, and so on. Well, if you go over here to this government report and you look at the sampling days, they begin at 135. Well, last time I checked, 135 lay between 68 and 210, yet there's no 135 here. Why? And you look over here in the government report, there's 274. Last time I checked, 274 lay between 210 and 321. Why isn't it there? And what happened to all these early stage intervals? They're not here at all. So, the first look at this thing is like, the sampling days don't match up. What did you do? So the only sampling interval that is actually similar are these 322 days in the 322 day sampling interval. And over here you've got a 321. Well, I've been told that if you started sampling on the 321st day and you continued sampling into the second day, sometimes they'd write down 321, and in other cases, they'd write down 322. So these are the same sampling interval. But if you actually look at the reported numbers, this one says 0.261, this one says 0.34, basically. You look over here, none of these numbers match up. These are both down around 0.25. Well, the closest thing to 0.25 you get is 0.26. And none of them are anywhere close to 3 or 0.34. So what happened there? Why did the numbers change? So again, we've got a very peculiar mismatch between what has been reported to the US government in some reports versus what has been published in the scientific literature. Now, kind of burying the lead here is these are the two published samples. The ones underneath the solid red here, those are these samples over here. But the samples in the red box at 1 molal magnesium chloride, 1.5 molal, 2 molal, 2.5 molal magnesium chloride, they just don't exist in the published paper. What happened to them? This is what happened. Those samples are something different. So this XRD scan on the left, this is from another government report, the same samples. So this scan over here on the left is an XRD scan of the most dilute magnesium chloride solution. It's one of the samples that was published. And if you look at the XRD scan, all of the peaks match up with the reference standard peaks for a mineral called chalconite. Well, chalconite is a dehydration product of borax. You can produce it during the sample preparation for the X-ray diffraction analysis. So I'm not going to cry about this mineral not matching up with the borax that was used in the original experiment. Keep in mind that, or remember that borax was introduced into the samples to react with the magnesium chloride. He's claiming that the product was a sodium hexaborate versus the tetraborate that borax is. So what this scan is showing is that the borax in the most dilute magnesium chloride solution remained as borax. Not surprising. Conversely, on the right here, we've got an X-ray diffraction scan of one of the samples at a higher magnesium chloride concentration. And this is one of the samples that was omitted from the published paper. And the blue lines are the reference peaks for a mineral called indorite, which is a magnesium borate. And so if you introduce borax into magnesium chloride, you can produce this magnesium borate mineral, indorite. And that's what this X-ray diffraction scan shows, is that indorite is effectively the only mineral in this sample. But indorite is clearly not a sodium hexaborate. That is contrary to his preconceived conclusion of what was going on in his samples. So he just left those samples out. They directly contradict his hypothesis and his conclusion. So he omitted 66% of his samples. Again, falsification. So this is my last sample or last example. And in this case, same guy, strangely enough, purported to publish the solubility of lead carbonate in various carbonate solutions. So he's got two data sets. In one set of samples, he's got a mixture of sodium chloride and sodium bicarbonate. And his other set of samples, he's got sodium bicarbonate and sodium carbonate, no sodium chloride in these. And so he's claiming, he explicitly states in the paper that he's measuring the solubility of cerussite, which is lead carbonate. And he explicitly states that there was no phase change during the experiment and that he analyzed the solids before and after the experiment. So we come over to a paper that was published again, roughly 40 years ago. So again, no secret. If you put these lead minerals into a sodium carbonate solution, you produce a double salt. And in nature, it's known as the mineral abelite. The guy that published this purported cerussite solubility measurement, he cites this paper. Apparently, he didn't get past the first page. Well, actually, it is the first page that makes this statement. And he should have known, if he had actually read the paper he cited, that his experimental conditions would have formed this mineral. Oops, wrong button. So I've got a cartoon here of the sodium bicarbonate, lead carbonate water system. It's not quantitatively correct, but it's good enough for government work. So over here on the right-hand side is a chemical reaction that should form the sodium lead carbonate hydroxide. And its composition lies over here on this tie line between sodium bicarbonate and lead carbonate. And so the phase fields where you should have only one solid plus solution should be very narrow. So there's a sliver over here on this left-hand side, an even smaller sliver over here on the lead carbonate plus water side. And then you should have a single solid in equilibrium with liquid with this sodium lead carbonate hydroxide that occurs here in the middle. So we don't know exactly how far into the interior any of these things go, but given how close these things are to the apex and kind of common sense, it makes them small. So most of this phase diagram, so this is mole percent, goes out to 100% of each one of these things. Oops. Most of the area in this phase diagram should be two solids plus liquid. Now these orange dashed lines down here they represent the range of compositions that were used in the experiment. So his sodium bicarbonate, his maximum sodium bicarbonate solution is down here. And the way I've drawn this cartoon, it should be his maximum carbonate composition should be up here closer to the Noccolite stability field. So we go down here. So I blew up that corner of the phase diagram. So this is just a expanded view of the previous phase diagram. So it captures, this 2 solid phase field down here, 2 solid phase field up here. Those are the brown things. Then the abelite single solid plus liquid phase field is here. And these orange dots are close to his actual reported sample compositions. And the way I've drawn my cartoon, this is just my interpretation of the way things should look. His compositions all but this most dilute one lie within the single solid plus liquid field. Now, one thing we do know, we know the position of this dot. We know the position of this dot down here. Because of the scaling here, these aren't particularly accurate. The point is to show that they're very, the concentration of lead and carbonate in this thing is not very large. So this sliver down here has to be very, very narrow. The homogeneous liquid field also has to be fairly narrow. It has to lie to the left of these data points. So we know it's narrow. Unless this point in the interior moves strangely down, you would have to have these points all lying within the single solid plus liquid field. Now, I'll point out that this guy down here, he's claiming that it is in the lead carbonate plus liquid field, one solid. The way I've drawn the cartoon is that it's a 2 solid plus liquid field. Now, it could be wrong. My cartoon could be off by a smidge, and this could be down the single solid field. Well, actually, you'd have to move this point up, not the data point down. But it's possible. But again, I go looking through the government report literature, and lo and behold, this is an X-ray diffraction scan from the government report. Again, he didn't report these things in his actual published paper. He just makes the claim in words with no substantiation. So this is the most dilute point, the one I just said, I could be wrong. Well, the X-ray diffraction scan says I'm right. There are 2 solids in that sample. One is the solid he claimed, which is cerussite, but there's this sodium lead carbonate hydroxide mineral that shows up quite prominently too. And the cerussite peaks and the abelite peaks don't line up. So it's not like you can mistake one for the other. They're both there. If you go to his more concentrated sodium carbonate samples, the only solid in this sample is abelite. Every single peak matches up with abelite. So what I showed over here, that these samples in here line in the single solid plus liquid field, that is in fact what you see in these X-ray diffraction patterns. Every single sample other than that most dilute carbonate sample contains only abelite. So again, looks falsified. Now, I pointed out previously that there's 2 sets of samples. One contains sodium chloride and the other one just contains carbonate. So there's 12 samples in each data set. In the first data set, those data are what he claims they are, with the exception of one sample, which also mysteriously contains abelite. And some people have focused on only that one data set and say, well, gee, only one of his samples is not what he claims it is. This is all good. Well, those people never bothered to look at the second data set where every single sample, all 12 of the samples, contain a bellaite, and 11 of the 12 samples only contain a bellaite. So this is my conclusion. And the bottom line is here is that if you see some funky thermodynamic data, there's a chance that it's not just bad, it's just not what the author claimed it was. And, you know, I showed at the very beginning that there were 70 chemistry papers retracted in 1 year because they were falsified, and that gave you a number of 0.04%. Well, I found one paper myself in that year that was clearly falsified. So I do not think that I just happened to find 1 out of 100 papers that's falsified. You know, so that's why I think that that 0.04% number is vastly too small. So the bottom of this is just, you know, the pre-publication peer review process, I think has largely failed. I'm not saying that it shouldn't be done, but I don't think it's working. And so the only way I see to address the failures of the pre-publication peer review is to do it post-publication. And there is a tool, I'm not sure how many of you are aware of it, but it's PubPeer. And it's mostly biology now. And you know, Elizabeth Bick, who I pointed out earlier, is a prolific contributor. So most of the stuff on PubPeer is biology. I would suggest to them that they categorize their tool so that it can be broken down into biological and chemical, material science, and so on. But you know, it's run on a shoestring budget. People do it on their own time and money. But it is a way where experts in a particular field can, if they see flaws in a published paper, they can pick them out and post them. And if you're afraid that this may hurt you during your own peer review processes on grants and publications, you can do it anonymously. And they have been sued because some people don't appreciate critical comments, and they have sued PubPeer to divulge the identities of the commenters. And those people have failed gloriously. So I think it's pretty safe to say you can preserve your anonymity if you so choose. Elizabeth Bick happens to post under her own name, and she does get sued a lot. And God knows how she manages to pay for all the lawyers, but she's a brave lady. You can say nice things about people on PubPeer. It happens less frequently. I have posted something on PubPeer where I said nice things about one of the people in the current audience. I hope they don't take that as a bad thing. So that's what I have to say. Make use of it, please.
So thank you very much, Charles, for your very interesting presentation. I don't know if you can just stop it in order to see everybody that is with us, and
okay.
and the presentation is for discussion. So I would like to ask the audience if anybody wants to do a comment or a question. Please, Hala.
I hope you you can see me now. Yeah.
Yeah.
Okay. Charles, thank you very much for all this interesting presentation. And I just want to comment that during our work with journals, we see a lot of bad stuff going on. We periodically see data manipulation. For example, NMR spectra are modified. For example, bad peaks removed or something like that. Or we see shifted data after we identify some problems, and we see a lot. So, and one of potential remedies for this is to make journals to publish the whole sequence from the very beginning of submission paper through all revision stages, so that readers can see the development of the paper. So in this case, the original data and potentially modified data can be revealed by comparing the old and new results. So because sometimes problems are changed, sometimes data are manipulated immediately as soon as paper is submitted, like the cases probably you described. But sometimes the manipulations happens during the review because problems were revealed.
Yeah.
So, and this publication of the whole sequence will probably guide through this potential manipulation potential.
Yeah, I'm sure you've seen a lot more than what I have, and keeping blessings upon you and your colleagues. Um, I I just know exactly what you're talking about. Things like, uh, well, any kind of spectra are very prone to manipulation, and I've seen a lot of it, including this same guy that I was describing in several of my examples. He's also manipulated his own X-ray diffraction analyses, and one of you talk about making peaks inconvenient. Peaks disappear in NMR spectra. Another thing people like to do is shift peaks. They literally take the entire scan and move things over, and so you start seeing gaps between the beginning of a spectra and the axes on a graph and so on. They're little things that show out or show up, and most people dismiss them. They just think they're little things. But usually little things are a hint at bigger problems. So
And I think Vladimir,
I would just add another thing about PubPeer. It's when you point these things out on PubPeer, it is moderated. You can't just go on there and start trashing people and being mean. You actually have to have evidence to substantiate your claims. So one of the great things about PubPeer is there's a little plugin that goes along with it. And so if you're searching the literature, you go on Google Scholar, or you go to a journal website and you're looking for a paper on a particular topic. That plugin tool alerts you to any papers that have been flagged. And it's a good, if you're a graduate student and you don't want to get led down the garden path on bad research, or you want to find out what the problems are in a particular area, it's a great tool for that. It should be a teaching tool. Anyway, sorry, went off topic.
Thank you, Charles. It's a good suggestion.
thank you. And also in the chat, I will drop one paper. I believe it's everyone can access it. So it's about one case when the paper was found to be. It's the second part. There are two articles on the same page, and the second article, and it's the case when the data were found to be falsified, and the researcher trying to say that the data were lost. They were eaten or something lost in a cow poo. Because the research was on methane production of methane from cow poo, and they said that all notebooks were just lost in this in this garbage.
Yeah,
the
that's the most common response when people get called out for having suspicious data. It's that data is so old. We had a fire in the building, we had a flood in the building, our computers were destroyed. I've moved to a different institute. It's I'd say 80% of the time at least, people claim that they can't find the data that has been called into question. Another thing you reminded me of was because of all of the attention recently with scientific misconduct, some of the people pointing out the misconduct have also been found to have produced falsified data. So there's a professor at Harvard, as we speak, who got called out by a group of statisticians, one of whom is at MIT, and I can't remember where the other two guys are from, but they pointed out that this professor at Harvard that had written a fairly high profile paper about scientific misconduct had falsified her own data. And so she's suing them. Even the university isn't backing her, but you can get mired, when you call these people out. It can turn into quite the battle, and sometimes the people that are calling out the misconduct are doing it themselves. Anyway, another off-topic comment.
So let's spend our discussion because Vladimir wants to present some comments also and a question. Please, Vladimir.
I will try to be short. It's difficult to stop because I could talk for hours about this. My own conclusion is that in our area, reporting property data for substances and mixtures, 50% approximately of publications are nothing but noise. 50% of already accepted and published. And Charlie presented the ultimate case of falsification, but in most cases, people don't care. And the culture of research, I believe it's the lowest in the history now. And the question is, who is interested in getting correct data? Who is motivated to make changes, and who has power? Unfortunately, people who are interested, they don't want to invest anything. People who are motivated have no power. People who have power don't care. And this is the topic of my presentations on 2 European conferences last month. So I have some ideas. I haven't lost hope yet, though many things I tried failed, and I don't repeat them again. I'm trying to find new things. I want to mention a couple of publications. We made a publication on data reliability. We call data validation. And Charlie, you probably know Kirk Nordstrom from USGS.
Yes, I don't know him personally. I know of him. So
he has the word validation, and I would say what I call validation, it's gradual invalidation. The more information we have, the worse the data appear. And another paradox is to validate data, you need to not need it, like in a bank. The bank is a place where you can get credit if you prove you don't need it. You can prove the data if you don't need it, if you know the value without this data. And my other publication was a perspective paper in fluid phase about scientific publication in digital age. And there are some problems, some ideas. So to stop, I need to stop myself. So if anyone is motivated, I would be happy to collaborate to search solutions together. Please contact me. If not directly, you can contact me through CIMAO, for example.
Sure.
Thank you.
Sure. Thank you very, very much for your participation, Vladimir. It's always a pleasure to have you with us. Also, I'm going to move to Wolfgang, please.
Thank you, Charles, for these interesting examples. Now I understand why you need so much time for the lab. But I'm not so convinced that this tool you mentioned, the pub peer, is so very helpful, because I don't like the anonymous comments, because you don't know how qualified this commenter is really. So you can even generate more confusion. if this qualification is not good enough. Another thing is, I think thermodynamics has a good feature because many quantities are interrelated, and you showed a good example with the lead oxalate, and you can find out there's something not correct. And in the old times, then you had to repeat these measurements and by another group, and then you find out the truth may be. And if you find an author who has 2 times published wrong data, then he was disqualified and nobody was longer reading his papers. I think this, but in modern time, this way is, I know, very difficult to, to proceed.
Yeah, so you've covered a few points. So one about the pub peer anonymity aspect. So when I review papers, none of the papers that I've reviewed recently ask for the reviewer to be identified. So even in pre-publication peer review, anonymity is, I think, the usual case. You know, I can take a good guess at some of the people that have reviewed my papers, at least for the intelligent comments I get, I can take a good guess at who they are. For some of the more inane comments, God knows who they are. And people likewise can probably guess at me being a reviewer when I've reviewed papers. But you know, I think that's probably an exception rather than the general case. Now on PubPeer, a lot of people that have been flagged as providing suspicious data or substandard data, whatever, they do demand identity. They say, I'm not going to answer your comment until you tell me who you are so I can judge whether or not you're qualified to make the comment. Well, no, there's a reason why people do post anonymously, and that's because they don't want retaliation. And, you know, retaliation is real in all respects, not just pub beer. You know, I pointed this, you know, I'm aware of a lot of this stuff because of where I used to work, and I was retaliated against for pointing it out. So, you know, if you happen to be a member of the community and you point this crap out, some of those people in the community will shoot at you. And, you know, it ain't justified. They're just pointing a gun back and shooting. Now, as far as the other aspects about repeating the measurements and finding out that, you know, some data set is anomalous and probably bad, these are resources that are wasted. Now, I'm not saying that you should never repeat measurements. God knows, you know, there's a few thousand density measurements for sodium chloride, and 900 of them were probably pointless, but people do them because it sets a baseline for their other analyses. You know, it's a means of evaluating the quality of their other measurements. That's great. But in a lot of cases, money is expended on repeating experiments that, if you're just repeating them to evaluate another data set, it ain't necessarily a good expenditure of money. So, you know, there's that problem. Again, people gripe about funding. And if a funder says, well, that's already been done, why should I fund you to do it again? What are you going to go to them and say, well, I've got a suspicion that those measurements aren't good? And they're going to say, well, why do you think they're suspicious? And the funder isn't necessarily somebody that has any capacity to make that evaluation. Just like the people that are monitoring, you know, you get some accountants thrown on the process after fraud is exposed, and those accountants don't necessarily know anything other than accounting. They don't know in this case, they don't know the science. So how are they going to evaluate what the future work is?
Yeah, therefore, I think it's important also that we come a little bit back to the old tradition that the professor has a budget where he can decide himself what is necessary to measure.
Yeah, well, but so this is another problem
Yes.
I run into is
Yeah.
academics tend to think that they are the only ones doing science. And that's part of the reason why I pointed out the money thing at the beginning, is because there's a tremendous amount of money spent on basic research in industry that is largely unappreciated by academics. There's also an even greater amount of money spent in the US in federal research institutes. And I'm guessing that in Australia and Europe and so on, that there are similar institutions. And in these government-run research institutions, let's just say they're not very efficient. And so you can get people that are in positions where they are considered to be scientific authorities. And this happens in business and in government research institutions, where these people aren't, well, I won't be as harsh as I'm inclined to be. Let's just say they're not qualified to do their job. But they are there because people don't want to lose head counts in their organization. Now, that's a big deal in some organizations. You got managers who, that's one of their principal aims in life, apparently, is to maintain a head count. And so if you whack somebody because they're not doing things properly or they're doing fraudulent stuff, you've lost a head count, and you also get scrutinized for having somebody in your organization that was unproductive or doing fraud. And so that doesn't look good on you. You know, if you're a manager that's had somebody working for you for 10 or 20 years and it turns out that guy's a fraud, what are people going to think about you as a manager? So they don't want to get rid of those. This is one of the common problems with fraudulent science is the institution wants to hide it. The managers, mid-level people want to hide it. The fraudster certainly wants to hide it. The funders that were funding the fraud for 10 or 20 years, they want to hide it because nobody wants to be exposed as having not done their job. And even the journals, the publishers very frequently want to hide it. Yes. Because, if you've got fraudulent papers published in your journal, it looks bad for you. And so, it goes back to what Vladimir was saying, is that the people that are motivated to do this don't have any power, and the people that have the power to do something about it are not motivated to do something about it.
Well, thank you, Wolfgang, for your.
Thank you.
I think Hala wants to make some comment. Please, Hala.
Yeah, I wanted just to point at the one comment in the chat. So from Dory. So she, I think it's she. I'm not sure. So is it she or he? So about reporting raw experimental data and as much detail as possible for reproducibility. If this information is provided, it's I would say it's more honest reporting, and you can track if there are some issues with experiment, with the data. But if everything is hidden, it becomes really difficult.
Yeah, well, that's a very good point. So in this era where electronic storage is dirt cheap, journals should be, the editors, everyone should insist that is raw as possible. Some data is so raw that you can't make heads or tails out of it unless you truly want to spend a lot of time figuring it out. But things like in the cases I showed, the X-ray diffraction scans for all of the samples should have been included in some sort of supplementary information. And, in some of these cases, what people do is they post or they publish some representative analysis. Well, in my jaded old age, what I've come to take representative to mean is that this is the one that shows things that we like most clearly, and the other stuff shows things that they might not look so good for me, so I'm not going to show them. And in this case, the individual showed, when he shows representative samples, he only shows those samples which bolster his case, and he completely leaves out the stuff that contradict his argument. So, that's why I think.
And also, sorry, just one more question about samples. For example, the XRD patterns, they fail to describe frequently how they dry the samples. If you dry samples incorrectly, you may lose water or solvent or whatever is part of the crystal structure. So you're losing solvates, you're losing information about hydrates, and they fail to report this simple information, how they dry the sample.
Yeah, well, that's why I pointed out in that one case where the XRD analysis showed a dehydrated mineral, but that dehydrated mineral was consistent with the mineral that they claimed, or not claimed, but consistent with the mineral that they initially used in their experiment. So in that case, I can say, okay, I can explain this analysis away. If I was trying to defend the work, I would say, okay, well, here's a defense. This defense is logical. I'm not such an ogre that I'm going to say, oh, no, that's fraud. If it's a defensible argument, I'm perfectly happy to accept it. And your argument is the same as mine. Well, kind of. There are cases where it's not going to work out so neatly, but people need to present more details about their studies than they do. I recently dunked on a paper because they boiled down a calorimetric analysis to 5 lines, when there are many decades of people that have published entire papers on the topic that was boiled down to 5 lines. And, to me, it's just not acceptable. You have to provide the details of your experimental methods and your analytical methods.
Well, Vladimir wants to do a question. I think we have around 10 minutes to continue our conversation today. And I would like also to introduce some comments, taking into account that today we have many PhD students and people starting their career here listen to us, and the idea that Vladimir was saying about that we cannot do anything because the people that have power are not interested on that, and all the people that are interested on that are really with any power to solve things. I don't believe that, because we all have the power to do something, even if it is when you do your revision of the work of your students, when you do the revision of the work of other people. And I have also to tell you that is quite very important for students to know that even if you don't are like having a big impact in terms of what you are doing, if you do some mistake, it cannot be anything worse than have your colleagues looking at you, saying and looking at you as a person that are publishing things that you cannot believe in. So in my view, there is also this kind of things that is related with the formation and the ethics of the people and the PhDs and all the people that works with us. Of course, times are difficult, and I know I will give you the word, Vladimir, but before that, I have to share also this opinion. Times are difficult because editors should be a little bit possibly more responsible for what they publish there. Then we have also the journals that now people are asking for article processing charge everywhere, so you can also pay your publication. So in a certain way, nowadays is quite even more difficult to control that, but we have all the responsibility, and it's why you are doing this. You at NIST are doing a great job, and I thank you for sharing the articles you said. You uploaded that to the chat, because you are doing a great job, and you help us all in terms of selecting things or doing the things in the right way. Of course, we always have in all things in society a certain percentage that I don't know if it is 4% or if it is 50%, possibly is around 10%, that are people doing they are criminals. So the thing is, here is about the same, but we have really the responsibility to do our job as a reviewer. And as you know, Vladimir, these days, and Charles, the number of people sending you papers to review is difficult, because you receive many each week, and you cannot accept everything. But we have the responsibility to share with these young generations about the need of being really very truthful and look into the things in a ethic way, and look into the things in a way that they are doing and are spending money, public money or money from the companies. And what is important is to have the results that are showing what nature is behaving. That is the most important thing. So be aware to look at someone that are reinventing your results, or creating or just copying the result. I also saw that, of course, Charles. I also saw some papers that they were already published, the data exactly as the way you showed today. But the thing is that in that case, I reported to the journal, and I was expecting to have some consequence of that. But in fact, in that case, I did not. So the fact is that sometimes when I talk about editors, I'm talking about the policies of the big companies that are managing science now, that are looking for profit and for money, but we have the power to change and to give the right information to our students, to the people we work with. And if you create this net of connections, we can do a lot. And sorry, I took some of your Vladimir.
Oh, that's it.
But I had also to share my view with you. And I would like also to hear something about this with you, or discuss a little bit. But Vladimir, please do your comments.
Okay, I will be very short. Once again, I tried many things, and I'm sorry to say that working with publishers and editors, I decided there is no way to expect anything from it. I exhausted my options. I'm an editor also, but I have some other ideas, and I will invite you and Charlie to my new initiatives, and to bring some fun. First of all, my conclusion as a user of this information, we prepare data for chemical engineers. We consider scientific journals like social network works, and try, in the absence of information which needs any data we consider unnecessary, we just try to figure out the pattern and reveal reliable bloggers and not reliable bloggers, and expect accordingly. And other thing, the site which Charles shared with us today, you know, if you ever encountered bad bugs, and it is trouble last years, there is no way to avoid it, because officially there's just no way. But people created some websites like bad bug registry, and you, before travel, you can just visit and decide where to stay and where to avoid staying. And I would say it's PubPeer. It's kind of bed bug registry in research community.
That's a fair comparison. I feel bad for the people that do good work that have show up on PubPeer, because there really are people that do say complimentary things about people on pub beer. It's just that so many more are bad things. I want to get back to incentive to exposing fraudulent research. In the US, and as far as I can tell, the US is fairly unique in this way. There's a type of lawsuit which falls under a law that's called the False Claims Act. And this was something that was passed by Abraham Lincoln during the Civil War, the American Civil War. And the law was intended to give incentive to private citizens to combat fraud amongst people that were principally supplying supplies to the army. It's just what I said about any time you funnel large amounts of money, government money, into something, fraudsters are going to try and take advantage of that. In that case, there were a lot of fraudsters that were making substandard uniforms and so on for the army. And so to combat that fraud, Lincoln and Congress passed a law that said, okay, anybody that comes forward that can point out fraud from a government contractor, you get to keep somewhere between 10 and 30% of whatever we recover. So in that Duke case, that Duke fraud case that I pointed out, that was one of those False Claims Act cases. And so there was some guy that worked in the group that was doing the fraud, and he got in cahoots with the funding agency and said, I'm aware of some fraud going on and your money that's being wasted. And his brother happened to be a lawyer, so that was very convenient for him. And then the FBI got involved. And so they did things like record some of the conversations in the group where they were discussing doing fraud and so on. And so they basically had the fraudsters, to be crude about it, by the short hairs. And so that's why the government had to cough up the $112 million. And so the guy that pointed out the fraud, that had the evidence of the fraud, and the government got the government to pursue this case, he got to keep something like 25% of that $112 million. So that's the kind of incentive that I think is the most effective way of fighting this fraud. Money always talks. And so if you want to get people to actually engage in doing something about it, you got to get the government to kick some of that back to the people that are pointing the fraud out. In the US, this happens. I'm pretty sure in the UK, it doesn't. I'd be willing to bet that the US is unique in this particular way. So you want to do it in other countries, do something like that. Now, I'll back off a little bit if it makes it sound like I'm going yah for the US. I'm not, because it's rare, extremely rare, for the US government to pursue scientific fraud. That Duke case and one of the other Duke cases that, I think it was like $30 million, those are extraordinarily rare cases. They pursue lots of False Claims Act cases, but rarely does it involve science. And it goes back to judges, juries, and lawyers don't do science. And so if you start pointing out that the fraud is scientific, they say, well, show me a direct tie between the funding that we spent on the science and the fraud that was done in the science. Most scientists don't have access to the accounting books, so they can't make that direct connection. And the government says, well, thanks, we feel bad for you, see you later. So anyway, the laws need to be changed to both give incentive and make it easier for people that are pointing out wasted money in science to actually do something about it.
Thank you
So
very
if you-
much, Charles. Thank you. It is really important discussion today, and we should all thank you for your presentation and for being here with us. It was really a very nice discussion. We have limits on time. People are just asking to leave, but I have like a last word of hope, because I understand as far as we were talking, we are always looking to do things better, and we are always to do things in the right way. So let's teach our students, our PhD students, our graduate students about the beauty of representing the nature and look into what nature gives us in a truthful way. And I think this is the message that is a very a good way to finish today. Thank you very much for your participation, for sure, Charles, and everybody that was attending today. Was quite a very interesting day for us. I believe I can talk for many of us. And so let's thank you again, Charles, and hope to see you in one of these new activities soon. I will share the information soon. Thank you very much. Goodbye.